In 7.4, we're going to do two things. We're going to measure arc length, or length of a curve, and we're going to measure surface area. In 7.2 and 7.3, we looked at taking a closed region and rotating it around an axis. In 7.4, we're going to look at taking a curve, rotating that curve around an axis. And if that's not closed in, we're not going to have any thickness, but we want to find out if we rotate that, what would that surface area be? So you think about rotating that around the y-axis. That would give us like a cup. We're not going to find the volume of the interior area or interior section. We're just going to find out how much surface that has. When we talk about arc length, we're talking about if we have some function and we want to know the length, if we were to follow that path from one point to another point, what would that length be? So not the direct distance from this point to that point, but if you were to follow that curve, how long would that be? If you had a string and you laid the string along that surface and then you measure that length, how far is that? So we're going to use smooth curves. We're not going to have any curves that have sharp points in them, because when we have sharp points, we have places where our derivative of that is undefined, and that makes some issues. So let's look at how are we going to be able to find these lengths. So let's suppose we have the curve, and we want to find the length or the distance from here to here. Then if we were to break this up into little segments, we can find the straight line distance from here to here if we know what the change in the x is, and we know the function. So if we know the change in the x and the function, we can also get the change in the y. X and y are perpendicular, so the distance between those two is the change in x squared plus the change in y squared. So that equals that distance squared. So if we want that distance, we take the square root of both sides. So that distance is the square root of delta x squared plus delta y squared. We're going to add those up from one side to the other, from A to B, and the closer and closer we let these points get, the closer, the more accurate our calculation is going to be. Notice here, from here to here, our curve doesn't exactly follow the line, so the actual distance the curve travels is a little bit farther. And to get that more accurate, we let it get closer and closer. So we're letting our delta x go to 0, or you could say our number of intervals we're letting go to infinity. So summing delta x squared plus delta y squared. So if we let our number of little sections, little line segments, go to infinity, which means the width of each one of them is going to be very, very small, then that goes to the exact length of our curve. So remember that those sums translate to definite integrals of delta x translates to dx, delta y to dy. So if we want the length of that curve, It's that integral. Now let's do a little bit of work with this because getting dx and dy, that's a little not exactly the way we want to handle that. So inside that square root, let's factor out a dx squared. So if we factor out a dx squared goes into that one time, dx squared goes into that dy over dx squared times. So that's the integral from a to b. We have two separate square roots here, so let's call this the square root of dx squared times the square root of 1 plus, instead of dy squared over dx squared, let's call that dy over dx all squared. The square root of the square cancels, so we've got the integral from a to b of 1 plus dy over dx, which if our function is called f, we'll just call that f prime of x squared, move our dx out to the end. So that's how we can calculate our arc length. 1 plus our function's derivative squared, take the square root, dx. If it turns out our function is in terms of y, then 1 plus the derivative of our function with respect to y squared dy. So let's look at an example. Let's suppose we have y equals x cubed over 6 plus 1 over 2x, and we're going from 1/2 to 2, and we want to find the arc length there. So just a quick sketch of that. If we put a 1/2 in, we get, what's that? 1/2 cubed is 1 over 8 divided by 6, so 1 over 48. If we put a 1/2 in here, the 2 and the 1/2 cancel, giving us 1. So 1 and 1/48 when we're at a half. When we're at 2, if we put a 2 in, 2 cubed is 8 over 6, or 4/3. Put a 2 in here, 1 over 4. Let's see, common denominator of 12. So 19 over 12, it's like 1 and 7/12. So we're going to have a little curve, kind of like that. So if we want the length of that, we need our derivative. Let's just call that function f of x. So we want the derivative of that. So let's rewrite that as 1/6 x cubed. Bring the 1/2 out, bring the x up, x to the -1. So if we take the derivative, we bring the 3 down. 1/6 times 3, or 3/6 is 1/2, x to the 1 less power. Bring the -1 out front, so that's -1/2, x to the 1 less power, so at 1 less than that would be -2, or we could say over x squared. So that's our derivative. Both of those have a 1/2 in them, so we could, if we wanted to, factor a 1/2 out and say a 1/2 x squared minus 1 over x squared. So if we want our arc length, we're going to integrate from the left side to the right side. 1/2 to 2, square root of 1 plus our derivative squared. Dx. So let's come over on another sheet and let's square our derivative. So if we square our derivative, we have two terms, so we square the first, square the second. I say two terms, two factors. So if we have a product, we can square those separately. So it's the first one squared, so 1/2 times 1/2 is 1/4. Times, if we square this, it's the first one squared, x squared squared is x to the 4th. The product of these twice, so if we multiply these together, the x squareds cancel, giving us -1, so that twice. And then the last one squared. So negative times negative is positive. 1 over x squared times 1 over x squared, 1 over x to the 4th. A couple things we can do here. We can leave it like that, or we can try to get a common denominator. Let's see. Let's just put this in first. So let's see, let's copy that. Copy that, come over here. So our S is square root 1/2 to 2 of 1 plus what we just calculated. Oops. So I can drag all this over here. Times dx. So S equals square root of 1/2 to 2, 1 plus x to the 4th over 4 positive times negative is negative. 1/4 times 2 is 1/2. 1/4 times x to the 4th, 1 over 4 x to the 4th. So if we wanted to, we could come in and get a common denominator. So our common denominator would be 4x to the 4th. We think of all of these as fractions. For 2 and 4, the common denominator is 4. We have an x to the 4th. So this one is missing all of that, 4x to the 4th. This one is missing an x to the 4th. We already have an x to the 4th on top, so if we multiply top and bottom by x to the 4th, that gives us x to the 8th. This one is 2. We need to multiply it times 2x to the 4th on top and bottom. This one has it all, so plus 1 dx. So S is the integral from 1/2 to 2. Square roots, we have 4x to the 4th minus 2x to the 4th. So 2x to the 4th. We have plus x to the 8th, and let's see, let's put that out front because that's the largest degree. Plus 1 over 4x to the 4th. Now, that numerator factors. To get an x to the 8th and an x to the 4th in the middle, we can do x to the 4th times x to the 4th. To get a 1 here and a 2x to the 4th here, plus 1 plus 1. So if we have something times itself, we can say we have that squared. Now notice the numerator is something squared, and we can take the square root of the denominator. So if we take the square root of the numerator, the square goes away, leaving us x to the fourth plus 1. If we take the square root of the denominator, the square root of 4 is 2. The square root of x to the fourth is x squared. So we can take, to make this something that's easy to integrate, let's take each term on top divided by our denominator. So x to the fourth, and we can pull the 2 out front, call that a 1/2. So x to the fourth divided by x squared. 1 divided by x squared is 1 over x squared, or we can call, or x to the negative 2. Now, of course, that's a simple integral. That's x to the 1 greater power over that power. This is x to the 1 greater power, so x to the negative 1 over negative 1. So s is 1/2 x cubed over 3. Move the minus out front and call that minus. Move the x to the denominator, 1 over x, evaluated from 1/2 to 2. Which just means we plug a 2 in. So 2 cubed over 3 minus 1 over 2. Plug a 1/2 in. So 1/2 cubed, that's 1/8 divided by 3, so 1 over 24. Plug a 1/2 in. 1 divided by 1/2 is 1 times 2 over 1, so times 2. And then, of course, just simplify that. 2 and 8 reduces, giving us 4/3. 1/2 times 1/2 is 1/4. 1/2 times 1/24 is 1/48. 1/2 times 2 is 1. So what's that? 4/3 minus 1/4 minus 1/48 plus 1, common denominator of 48. So times 16, so 64. This is times 12, so minus 12. This is 48 over 48. So 48 on bottom. Let's see, 64 minus 12, that's 52, 51, 51, and 48, 99. Now that does reduce. 3 goes into 99, 3 goes into 48, and that's as far as we can go with it. So that is the length of our curve as we worked along that path. So the simplification was a little messy, but it was all the integral of the square root of 1 plus our derivative squared from the left side to the right side. So the messiest part here is not necessarily coming up with our formula, our integral. The messy part here is just going to be integrating. So take your derivative, then square it. Then you're going to have some simplifying to do underneath your radical. So do a little bit of algebra. Generally, you're probably going to end up with something that you can take the square root of. Then take your antiderivative, plug your numbers in. So that's calculating your arc length. Next thing we'll do will be to look at calculating surface area. So now that we've found the length of a curve, Let's go and look at finding the surface area. So if we have a curve, we discussed this earlier, we could rotate that curve around whatever axis, and that's going to generate, like this one generates some veil, and it's going to have a surface. So we want to calculate that surface area. So if we look at taking a small little piece, say this was our curve, let's take a little bitty piece of that, and let's rotate that around. If we take a small enough piece, rotate that around, it basically is going to look like a ribbon. You look at it from the end, it's not really going to have any thickness, and it's just going to be a ribbon. Think about like a ring that goes around the barrel, or like a ring goes on your finger. It's just going to be a little ring that has a little bit of thickness to it. That thickness is just going to be given by the arc length. And then if we look at down the axis, we're taking that little piece and it's going all the way around the axis. So imagine taking a ring. The distance around that is called the circumference. That distance is pi times the diameter, or 2 pi r. So if we want the surface area of that, imagine looking at this from the end view. Wrong drawing. If we were to look at it from the side, this element is going to be flat. And then that's going around in a circle. We look at it from the top, we said, looks like a circle. So if we want the surface area of that, we're going to take, if we were to cut it and unwind it, we would take the length, which the length is how far it traveled around, 2 pi r, times the width, and the width will just be whatever that length is. Notice it's not necessarily just vertical or just horizontal, so that's our arc length. So area, length times width, so length times arc length. Arc length, let's see, erase that. Arc length we calculated by integrating from a to b, square root of 1 plus f prime of x squared dx, or f prime of y squared dy, depending on whether there's a variable in x or y. We take that times 2 pi times our radius. 2 pi is a constant, put it out front. That'll give us our surface area. So again, your length, your arc length is the width of that ribbon. That ribbon is going all the way around, so the length of that ribbon is the circumference, where the radius is the distance from that sample element to the axis of rotation. So that's how we'll calculate our surface area. So let's look at an example. All right, so let's come over into Inventor. Let's look at a quick little picture. Let's sketch. Let's sketch a little parabola, parabolic curve, and let's draw the y-axis in here. Let's rotate that around the y-axis. So if we want to do a revolution, that around this axis, and we get this shape. Just look. Here's our curve, and then we're starting to rotate that. So there. So we're wanting to find that surface area. So we're not finding the volume, we're not finding how much is contained inside it, just what is the area of the surface of that. So let's suppose that our function is given by y equals x squared, or you could call that f of x equals x squared. So as our parabola, and let's go from 0 to 2 in the x direction. So we're going to rotate that. So our surface area, 2 pi, the integral from a to b of our radius in terms of x times the square root of 1 plus our derivative squared dx. So our derivative is 2x. So look at our radius. If we pick a sample element here as being a little piece of that curve that we're wanting to calculate the area of when we rotate it around, we rotate that around, this will be our radius, and that radius will be whatever particular x value we're at. So when x is 0, that distance is 0. When x is 2, that distance is 2. So our radius is just given by our x value. 2 pi, the integral from 0 to 2 of x times the square root of 1 plus f prime squared. So if we take our derivative and square it, it's 4x squared dx. So we need to evaluate that integral. Some of these can get really messy. This one's actually not too bad. Let me take that, let's pull it down here. If we pick what's underneath the radical to be u, then notice du is 8x dx. We've got x dx. We put an 8 there, divide by 8. That reduces to pi over 4 out front. We can call all of that 1 plus 4x squared to the 1/2 comes 8x dx. So du, u to the 1/2. So if we integrate u to the 1/2 du, that's u to the 1 greater power over that power, or times its reciprocal, plus c, and we're going to evaluate that from 0 to 2. We don't have to have the plus c because it's a definite integral. So our u is 1 plus 4x squared. So u to the 1 greater power over that power. So that gives us pi over 6, 1 plus 4x squared to the 3/2 from 0 to 2. So let's see what we get. We get pi over 6. If we put a 2 in, 2 squared is 4. 4 times 4 is 16. 17 to the 3/2 minus pi over 6 times, put a 0 in, we get a 0, 0, 1. We could factor pi over 6 out if we wanted to. 17 is not a perfect square, so we can't really simplify that square root, so just call that, we could call it the square root of 17 cubed. 1 to any power is 1, so if we factor a power of 6 out of that, we're just left with 1. So that's the exact area of that surface of rotation, or we could get that as a decimal. So the square root of 17 raised to the third power minus 1. I think I clicked the wrong button. Let's do it. So the square root of 17. Then we're going to raise that to the third power. Then we're going to subtract 1. So that's what's inside. Then we're going to do that times pi divided by 6. It's about 36.2 units, square units. So that's that particular surface area. Let's look at setting up the integral if we were to do that same problem, but rotate it around the x-axis instead of the y-axis. So rotating it around this way. Let's just see what that would look like. Need to come in, put an x-axis in here. So if we draw that axis, now let's rotate that curve instead around the vertical axis, around the horizontal. So notice we get a bell like that. We're wanting to find the surface area of that. It's kind of like the bell of a trumpet or a musical instrument. So we still have the same general formula. And notice we could have this where it was Rx and this f prime of x dx, or it could be a function of y, g prime of y dy. And that's going to have to do, is our function written as a function of x or a function of y? If our function is given as a function of y, then we'll do dy. This would be f prime or g prime of y, and then we would want this in terms of y. But if our function is given in terms of x, then we'll want to do dx, which means our derivative will be in terms of x, and so will this be in terms of x. So if we're rotating this way, and we draw our sample element in, then the radius will be from here to here. Now the distance from the x-axis up here, that's y. That's representing our radius, but that's a y value. And notice for different x's, y is given by this formula. So let's go back and say that again. So our radius, as a function of x, our radius is the distance from here to here. Well, that's whatever the y value is on this curve. And this distance is the y value on this curve. But on this curve, the y value in terms of x is the x value squared. So example, the y value here, if I put is 1, but in terms of x is 1 squared. The y value here is 4, but in terms of x it's 2 squared, so it's the x value squared, just using that function. So our s comes from the 1 plus f prime. F prime is 2x squared, so 4x squared. So our surface area, let's call this. Our surface area, if we're doing x, then we're going from here to here. Our r times the square root of 1 plus 4x squared dx. And don't forget, we have our 2 pi out. So that's our surface area. Let's just call that A. 2 pi, integrate from doing dx, so from the left x to the right x, our radius times the arc length. 2 pi, left to right, our radius, our arc length. Now that's a little bit messy of an integral to do, so we're not going to do that for now. I just wanted to go through how you would set up that integral, but I'll leave that for you for practice.